Good afternoon, sir.
Everybody is there. Good afternoon.
Good afternoon, sir.
Good afternoon, sir.
1 second.
Good afternoon, sir.
Good afternoon, sir.
Sir.
Just a minute.
Okay, sir.
Hello.
Yes, sir. Yes, sir.
Can you see the screen?
Yes, sir.
Yes, sir.
Okay. So
Sir, we can see it, but it's a bit hazy.
a bit hazy. No problem. No issue because it is. This is not regarding today's experiment. This is regarding the last day's experiment.
Yes, sir. I have
Okay,
a
sir.
query. Sir, we have a query regarding the last experiment, sir.
Yes.
Sir, in the last experiment, you instructed us to make the report, and I think Shoel had show you a draft report, sir. So,
Yeah, he has made the report. I told him also what he have to do. He has
yes, sir. And you instructed him that he needs to add
that report did not contain any sample calculation. That is the
yes,
wrong.
sir. Yes, sir. And he changed that. He included the sample calculation, sir.
Yes.
And sir, one more thing that I want to ask you, sir. Sir, you told us that we must add the derivation of the spherical.
That is because you see that previous experiment, if you do not give that derivation or if you do not give
Yes,
that
yes, sir.
one-dimensional steady
মানে স্যার এখানটা কি আমরা ধরে নেব যে প্রথমে ইকুয়েশনটা যেটা মানে ওয়ান ডাইমেনশন স্টেডি স্টেট হিট অ্যাকচুয়াল ইকুয়েশনটা ওটা ধরে নিয়ে তারপর আমরা ওই স্ফেরিক্যাল এর ক্ষেত্রে ডিরাইভ করব তাই তো
হ্যাঁ ওই থ্রি ডাইমেনশনাল you start from the three-dimensional general equation for heat transfer.
তারপরে স্যার ওখান থেকে করব
Two-dimensional conduction equation, general equation. Then from that you come to one-dimensional equation, removing the other two dimensions. Then from that you come to the spherical coordinate form, and there is a energy generation part that also you make zero. So finally you come to the equation, and from that equation using the boundary conditions you can come to the solution, right? That is one approach. That approach you can show that is good. And the second approach, whatever approach we had shown, whatever way we have done this thing, because this is a steady flow process, that's why for this we did not come, I mean in our equation we did not come from that one-dimensional steady state equation, isn't it?
Yes, sir.
লাস্ট ক্লাসে যেটা আমি পড়েছি তাতে তো আমি ওয়ান ডাইমেনশনাল ইকুয়েশন থেকে পড়াইনি, আমি একটা অন্য অ্যাপ্রোচ থেকে করেছি। সেই অ্যাপ্রোচটা এই যে শীটটা দেখছো এই শীটে আছে, ঠিক আছে? এই অ্যাপ্রোচটাও দেবে ওইটাও দেবে, দুটোই দিয়ে দেবে। থিওরিটা তো আগে চাই, কারণ এক্সপেরিমেন্টের মধ্যে থিওরিটা তো আগে চাই, সেটা দিয়ে তারপরে তো রিডিং এর থেকে রেজাল্ট, সেটা তো 2 লাইন।
Yes, sir.
You understand? All of
Yes,
you
sir,
do
yes,
not
sir.
understand Bengali, I think. So that is why I am telling you the experimental readings and the result. That is only 3-4 lines. That doesn't carry anything, you know. Sample calculation will become very small in that case. What I want is that you write the theory also, so that the theory and the sample calculations together make 1 page or 1.5 pages, 2 pages.
Okay,
right?
sir.
That is one thing. Second thing is the experimental results. Third is the instruction sheet as I have given you. And fourth is the graph.
Yes, sir. We have a query regarding the graph, sir. Sir, we have put it the experimental values in the Excel sheet, and from that we have get a graph, sir. But the thing is, do we have to take the best fit straight line curve for yeah, showing that graph, sir?
No. You have to plot the graph best fit straight, not straight line. You have to.
Sir, can I show
plot
you
the-
something,
You have
sir?
to plot the smooth curve either in the graph paper format or in the Excel sheet format, whatever you have done.
Yes, sir. Sir, can I show you something, sir, by sharing my screen, sir?
Later, you send your thing through in your group, then I'll see it. Okay.
Okay, sir.
Let me proceed with today's class first.
Okay, sir. Okay, sir.
So this sheet, as you can see, is regarding the last day's experiment. This I am giving to you because see, when the last day's experiment that was regarding a spherical shell, hollow spherical shell made of the insulating powder, right? Hello,
Yes, sir.
please respond. Otherwise, I will not be able to understand. Not, you see, this is the inner shell, is the inner diameter, that is the outer diameter, and we consider an elementary spherical portion. You see, this is the elementary spherical portion, right? I mean, part. We consider elementary sphere, and in that elementary sphere, we consider the steady state, steady flow, one dimensional equation format. Basically, this is the Fourier's equation. And from that Fourier's equation, because the heat transfer rate was a constant, because it is a steady state process, that's why the heat transfer rate is constant. So heat transfer rate is constant because it is a steady state process. Because whatever heat is entering in this through this radial distance into this element, same heat has to come out. Otherwise, the temperature of this element has to rise. Because the temperature is not rising, because the temperature is constant. So it is a steady state process. And because it is a steady state process, so that the heat transfer rate has to be taken as a constant. That is what we have done. And putting from the Fourier's equation, we have done it. I think this thing is clear to you. We have put the limits also in the integration, and we have got the equation. This is the equation of the K value. This K value is not mentioned in your sheet. In the report sheet, I mean the instruction sheet, there has been something wrong in the theory part, whatever they have quoted, they have written something wrong. I think they have not written this part. So you put that in the previous day's instruction sheet. That is okay. Now today, you understand, this is regarding the last day's deduction. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Anything else? Tell me.
স্যার আগের দিনে স্যার ম্যানুফ্যাকচারারটা আপনি আরেকবার বলবেন?
ম্যানুফ্যাকচারারটা হয়তো পলিল্যাব ইঞ্জিনিয়ারিং বলা আছে।
ওকে স্যার।
পলিল্যাব, POLYLAB, পলিল্যাব ইঞ্জিনিয়ারিং কোম্পানি। Acha, today's experiment is on measurement of thermal conductivity of metal rod. This is also another experiment on thermal conductivity. Last day's experiment was on insulating powder. How to measure the thermal conductivity of an insulating powder, that we had shown you last day. Today we are showing you the measurement of thermal conductivity of a metal rod. The metal rod might be maybe made of copper, maybe made of steel, maybe made of anything. What is the process? That is the thing that we are going to show you. Of course, there is an experimental setup. Let me go to the experimental setup. Before that, I'll tell you the objective of the experiment. Objective is to determine the thermal conductivity of a metal rod as a function of temperature. You know that for any solid, liquid, or gas system, there is a property like thermal conductivity, but the thermal conductivity is a varying property with temperature for a gas and a liquid. For a gas and a liquid, the thermal conductivity never remains constant, changes with temperature. But for a solid, it is a constant. It is taken as a constant. Why it is taken as a constant? It's not that it is exactly a constant, but it is considered as a constant because the variation is very small. The value of change in thermal conductivity in a solid with temperature is quite small. Now today we are going to investigate how much is the variation. of the thermal conductivity property for a solid metal rod. We are going to find out the thermal conductivity at a particular temperature. We are going to find out the thermal conductivity at some other temperature. And then we'll see how the thermal conductivity changes with temperature. That is our experiment. That is the first objective, to determine the thermal conductivity of a metal rod as a function of temperature. And for that, what we do? We just simply take a rod, we heat up at one end, keep the other end cooler, so that the heat flows and therefore the temperature changes from section to section. So, and now from section to section, we find out the thermal conductivity. So if we find out the thermal conductivity at one section, at one point, then we go to the thermal conductivity at other section, at other point. Definitely we are getting the thermal conductivities at different temperatures. Now we can plot that thermal conductivity with respect to the temperature. So that is the process of the experiment. I'll explain in great detail, but this is in a nutshell, this is the thing. Second thing is to study the temperature distribution along the length of the metal rod. This is very much experimental thing. We'll measure the temperature at different points of the metal rod under steady state condition. See, all our experiments that we are going to do in conduction are all steady state experiments. We are not going to make any transient state experiment. We are assuming that the temperature is not changing with time at any point. So that is the steady state consideration. Apparatus, they have made the apparatus here. I'll read out the apparatus later. This is the details of the apparatus. The make of the apparatus is Polylab engineering equipment. Can you see this sheet? Hello?
Yes, sir.
Okay, fine. Next, we go to the theory part. This theory part I'll explain.
Sir, should we consider the heat generation term, sir?
No, there is no heat generation internally. See, what we are doing is that we are heating up a rod. We are heating up a rod from one end.
Yes,
At
sir.
there is a rod of constant configuration, constant cross-sectional area. We are heating up only at one end of the rod, allowing the heat transfer to occur only along the length of the rod, one-dimensionally. The x direction, let's say, the y and z directions, there is no heat transfer at all. We are assuming that there is no temperature gradient also in the x, in the y and z directions. Only temperature gradient exists in the x direction. So with that idea, we are doing the experiment. There is no scope of any internal heat generation inside the rod. It is, see, when the internal heat generation will come, provided if you have a rod which is made of uranium. You have a metal rod which is made of uranium. Provided you are heating up one end of the rod and inside the rod also there is some nuclear fission going on. Then there is a heat generation. Then the boundary condition will be different. Then the equation will be different. If you have a rod which is heated at one end, cold at other end, and through that rod, suppose electric current is flowing, then there is also a heat generation. If you consider a rod where there is an internally there is an exothermic reaction going on, or an endothermic reaction going on, then there is a heat generation or a heat loss. So, but that term is not coming here because here we are having a rod made of metal, simply a rod of uniform cross-sectional area, which is heated only at one end. Other end is kept at a lower temperature. And that is the direction of heat transfer is along the length of the rod. Other directions of heat transfer are not existing. We are assuming that the temperature gradient is only along the length of the rod, not along the radius, not along any angular direction. The heat transfer occurs only along the length of the rod. So this is a one-dimensional heat conduction. That is one thing. Second thing is steady state. Steady state means that heat enters one cross-section of the rod. Then it goes to the next cross-section. Then it goes to the next cross section. Then it goes to the next cross section. Likewise, it goes to the different cross sections. Finally, it comes to the last cross section, and it leaves the rod. And when it does so, in every cross section, the temperature is same, uniform, along all the points in a particular cross section. That is number one. Number two is that it is steady. That means the temperature at any cross section of the rod does not change with time. That is the meaning of steady state. Let us come to the experimental setup. See here, we have got a cylindrical shell. This is a cylindrical shell, right? One end, and now this is the rod inside the shell. The cylindrical shell has an axis, and the rod also has the same axis. So the rod is concentric. The cylindrical metal rod is concentric with the shell. One end of the rod is coming out. This end is covered with a heater, electrical heater. It is heated. And this heat is flowing only in the x direction. That is the z direction, you can say. That is the length of the rod. On the other directions, that is the radial direction or any angular direction, there is no heat transfer. You consider the cylindrical coordinate system. In the cylindrical coordinate system, one coordinate is the axial coordinate of the cylinder. Here also, that is the coordinate along which the heat transfer occurs. And in the cylindrical coordinate system, there is a radial coordinate also. That there is no heat transfer here in the radial coordinate. No heat transfer in the angular coordinates. And this is the experimental portion of the rod, experimental length. Other ends are not experimental. We are not concerned about that. And the other part of the rod, which is again coming out, this rod is covered by a jacket, cylindrical. And in that jacket, we are circulating cold water. This water is coming. This is the side view. Water is coming, entering into the jacket. This diameter represents this diameter. So, and this outer diameter is regarding this shell. If you look from the side, one circle is for this, another circle is for this. And this is the entry, that is the exit. The entry, exit. Right? That is the water which is entering and leaving this jacket. And that is how the other end of the rod is kept at a uniform temperature. Acha, now you see in this cylinder. Acha, just a minute, just a minute.
অরণ্য মেশিন ড্রয়িং এর স্কেল কত নিয়েছিস রে?
0.5
হচ্ছে?
হ্যাঁ, আমার ধরে গেছে। যা ডাইমেনশন আছে সব হাফ করে দিবি।
আর সে তো যা ডাইমেনশন আছে সব হাফ করে দিলেই হবে, কিন্তু আমার অটোক্যাডে 0.5 ধরছে, কিন্তু তারপরে তো
অটোক্যাডে 0.5 কেন করতে হবে? অটোক্যাডে তুই স্কেলিং কেন করতে হবে? স্কেলিংটা স্যার বলেছে A4 সাইজ ধরানোর জন্য। অটোক্যাডের মধ্যে তো ইনফাইনাইট স্পেস পাচ্ছিস।
আরে অটোক্যাডে করার পরে সেই তো তুই A4 পেজেই
ভিউবোর্ডে করবি বলছিস, ভিউবোর্ডে করবি বলছিস, তাই তো?
হ্যাঁ, না না, আমি কথা বলছি যে তোর ওই টেবিলটা বানিয়েছিস না শুধু ড্রয়িং করেছিস?
দেখ আমি এখনো পর্যন্ত টেবিলটা বানাইনি।
টেবিল বানানোর জায়গা আছে?
না, টেবিল বানানোর জায়গা নেই। A4 সাইজে করলে টেবিল বানানোর জায়গা নেই।
হ্যাঁ, ওটাই আমি বলছি যে টেবিল বানানো শুধু ড্রয়িংটা ধরে যাবে, ড্রয়িংটা ধরে যাচ্ছে ভালো।
ধরে যাচ্ছে, টেবিল
হ্যাঁ,
বানানোর
yes.
জায়গা নেই, ইভেন তো নেম প্লেট লেখারও জায়গা নেই।
Hello.
ইয়েস স্যার।
Just one sec, I was not there. Now, as I was telling that, so this is the rod, okay, and this is the side which is heated. This is the side which is cooled. Cooled side means we are circulating cold water through a jacket. There is an inlet, there is an outlet. How much water is flowing through this? How much water is flowing per unit time, say per second? That can be measured. That we are measuring. That is how much water means how much mass of water is flowing. That we are measuring. And what is the temperature of the water at the inlet of the pipeline, and what is the temperature at the outlet? These two temperatures we are also recording. These two temperatures we are calling, this is T14 is the temperature of water which is entering, and T15 is the temperature which is leaving. They are measured by two thermocouples, which are the wires which are inserted here. And the wires are going into the control panel where we are taking the reading. And we have got another 13 thermocouples inside in this region. Now, this is the rod, as I told you. On the surface of the rod, we have got 9 thermocouples. T1, T2, T3, T4, T5, T6, T7, T8, T9. And this T1 to T9, the length between T1 to T9, the length of the rod between T1 to T9 is our experimental length. And outside this rod, between the cylindrical shell and the rod, there is a space. This space here we have packed with some insulating powder, let's say asbestos powder. So this cylindrical annular space is packed up with some powder, insulating powder, which here they are written as insulation. And in that powder, we have inserted 4 thermocouples. This is T1 to T9 here, and T10 is here, T11 is there, T12 is there, T13 is there. These thermocouples are inserted inside the insulating powder. And the lead wires are coming out. They are going into this is a thermocouple socket. From there it goes into the control panel. That we'll see. And what is this? Now you see the distance of these thermocouples 10, 11 and 12, 13, radial distance from the center of this rod. These radial distances are known to us. Now what is our experiment? Experiment is that this T1 thermocouple, this section we are terming as section CC. this section T9, we are terming it section AA. In between T5, we are terming as section BB. Now we are interested in finding out the thermal conductivities at section A, BB, and CC. Right. That is what we are going to do. Let us come to the next. This is another diagram on the modeling diagram. We are going to explain this theory. This is the experimental length of the rod T1 to T9. These are the thermocouples. They are at equal distance from each other, that is 22 millimeters each. And we have got another 4 thermocouples, T10, T11 here, T12 and T13 there. This is T10, T11, T12 and T13, and the distance, radial distance of T10 and T12 are same, that is 60 millimeter from the axis of the rod, and radial distance of T11 and T13 are same, that is, radial distance of T11 and T13 are same, that is 60 millimeter, and T10 and T12 are 40 millimeters each. Now, what we are doing is that, first of all, we are recording these temperatures, T1 to T9. When we are recording, not that just we start the experiment and then we record, not that. We start the heating and at one side. When there was no heating, temperature was same everywhere. When there was no heating and no cooling, right? No cooling also. Temperature was same everywhere. Now we started the cooling, we started the heating. And when we started the heating and cooling together, the temperature of this cross section and this cross section, they are maintained at different values. Initially, what happens? Initial condition is called transient state. That means heating has started, temperature has started rising from section to section. Heat is going from one section to another section. Initially, all the sections were at the initial temperature. But as the heat is traveling from one section to another, like say from this section to the next section, from this section to the next section, as the heat is coming, temperature is gradually raised in every section. That is how, when the heat comes to the last section, that temperature of the last section is also raised. And you will see that as the temperature changes in each section, all the sections are not attaining the temperature of the previous section. This section is not attaining the temperature of this section. This section is not attaining the temperature of this section. There is a temperature gradient. There is a temperature drop. Because this is continuously heated, and this is continuously cooled. And a steady state is attained when the temperature in every section attains a steady value with time. That means the temperature in this section is not changing with time. Temperature in this section is not changing with time. Temperature in this section is not changing with time, but they are different. Here the temperature is say 100 degrees. Here it may be 95. Here it may be 90. Here it may be 85. Like that, there is a drop. Finally, say here it is 50. So there is a drop in temperature, and the temperature at every section is not changing with time. That is called the steady state. When that is attained, it takes some time. Let's say after starting the heating, it takes say 1 hour time. After 1 hour, how will you know that this is steady state has attained? How will you know? We'll record the temperatures T1 to T9 at say 5 minutes interval. We'll see that when we record the temperature, we'll find that the temperatures are changing. temperatures of all the sections are changing. When the temperatures are changing, it is the transient state, so we are not taking the reading. When the temperatures have attained a normal constant value, then only you will say that the steady state has attained. Then only we will record. Then that is the steady state temperature. Then after the steady state is attained, we record all the readings 10, 11, 12, 13, and also 14 and 15. There is the water temperature also. Tell me any doubt about this? No doubt, I think. Now what we do, we are plotting this distance on a graph paper. So let's say this is the 0th point along X or Z, whatever you say. This Z is 22, Z is 44, Z is 66. That way it is increasing. And at every position, what is the temperature? Plot the temperature here, somewhere, let's say here. The next temperature may be slightly less. Next temperature may be slightly less. That way we plot all the temperatures on the graph paper. So we get a temperature versus axial distance, say X. Let's call it is X. So T versus X variation we get. Or you can say T versus Z. Let us say this is Z. I call it Z. Let's say Z. T versus Z variation we are getting. And from T versus Z variation, we will make the gradient or slope at this point. At this point.
Sir.
Yes.
So I can't see your cursor, sir. তোরা কি কেউ দেখতে পাচ্ছিস কারসারটা স্যার?
You cannot see the cursor.
স্যার মানে আপনি অনেকক্ষণ থেকে কোর্স মানে কোন সেকশনটাকে ইন্ডিকেট করছেন না আমরা বুঝতে পারছি না ঠিকঠাক।
আচ্ছা আচ্ছা দাঁড়াও দেখছি। হ্যালো, দেখা যাচ্ছে কি এই কার্সারটা দেখতে পাচ্ছ? হিটিং এন্ডের তলায় কার্সারটা রয়েছে। তোমরা কি মোবাইলে আছো না
ল্যাপটপে দেখছি স্যার?
ল্যাপটপ আছে।
সবাই দেখতে পাচ্ছে না, কিন্তু কেউ কি দেখতে পাচ্ছে?
না স্যার, দেখতে পাচ্ছি না।
কার্সারটা দেখতে পাচ্ছ না?
না স্যার, কার্সারটা দেখা যাচ্ছে না।
ওকে, ফরগেট দি কার্সার। এগুলো তো দেখতে পাচ্ছ, সিসি দেখতে পাচ্ছ তো? এই যে সিসি, এটা বিবি, এ, তিনটে প্লেন দেখতে পাচ্ছ?
হ্যাঁ স্যার।
T1, T2 এগুলো দেখতে পাচ্ছ?
হ্যাঁ স্যার, ওইগুলো।
T1, T2, T1 থেকে T9 of the temperature record করলাম. Then I plot a curve between temperature, the y-axis, and the z. This is the z direction and the x-axis. That curve I have plotted. Fine. Then I make the temperature versus dt dz at every section, like CC, BB, and A. Is it clear? আমরা একটা কার্ভ এঁকেছি, তো কার্ভ এঁকে তার তিনটে পয়েন্টে আমরা স্লোপটা বার করছি।
স্যার আপনি জেড ডিরেকশনটাকে কোন ডিরেকশনটা নিচ্ছেন? ওই অ্যালং
অ্যাক্সিয়াল
ডিরেকশনটাকে জেড ডিরেকশন।
সিলিন্ড্রিক্যাল কোঅর্ডিনেটে অ্যাক্সিয়াল ডিরেকশনটাকে জেড ধরা হয়।
ওকে স্যার।
আর যদি তুমি জেড না ধরে এক্স ধরতে চাও, এক্স ধরো, আমার কোনো আপত্তি নেই। ধরো এটা যদি এক্স হয়, তাহলে টেম্পারেচারটা যদি এই ডিরেকশনে হয়, ওয়াই ডিরেকশনে ধরো, তাহলে ডিটি ডিএক্স যে ভ্যালুটা, এটা যদি একটা কার্ভ হয়, ধরো মনে করো টেম্পারেচারটা আমি এই অ্যাক্সিসে প্লট করেছি, তাহলে তো আমি একটা কার্ভ পাবো। তো সেই কার্ভের ডিফারেন্ট পয়েন্টে, এই পয়েন্টে, সি পয়েন্টে, বি পয়েন্টে, এ পয়েন্টে আমি ডিটি ডিএক্স বার করতে পারি। সেটুকুই করব। এবার আমি কি করব? আমি একটা হিট ব্যালেন্স ইকুয়েশন করব আন্ডার স্টেডি স্টেট কন্ডিশন। at section A, whatever heat is flowing out at section A, that is cooling section, cooling end, whatever heat is flowing out, that is a QAA, Q suffix A, that is equal to minus K. K is the thermal conductivity at section A, area at section A, and dt dx at A. We can write like that. Let us see here. এই যে ইকুয়েশনটা, the
Yes, sir.
Fourier's equation, from the Fourier's equation we can say Q dot A, that is the heat transfer per unit time through section A into the cooling water, that is equal to minus Ka, thermal conductivity at section A, into area of section A, into dt dx, that is the gradient of temperature with x at section A. So this equation, we know, this is the Fourier's equation. Okay.
Yes, sir.
Now QA we can determine, Q dot A, how we can determine? Cold water is flowing through the jacket. We determine the mass flow rate of cold water per unit time, how much cold water is flowing through the jacket. Cp of water we know. Temperature temperature gain of the water, that is T14 to T15 in the thermocouple reading in under steady state, that we have recorded. So m dot Cp dt, from this we find out Q dot A. We put it here. A is known, from the rod area, is cross section is known to us. dt dx is available from the curve, temperature versus x curve. So we can find out K at the section A. dt dx, how we find out? Because we have a temperature versus x curve. Just imagine you have a t versus x curve at the point where section A is there. Just before that, you take any two arbitrary points very close, take the difference in temperature, take the difference in x value, find out dt dx. That is how we do it. So from this equation, we can find out the thermal conductivity at section A. Is that okay? Now we go to section BB. Come to section BB. In this section, whatever heat is entering in the x direction, because we are neglecting other, it is considering a one-dimensional heat conduction. So whatever heat is going in this direction, that is Q dot BB. Now, through this rod, we are not assuming any heat transfer in the other directions, right? But from this surface, we are assuming heat, we are considering heat directions, heat flowing in the radial direction through this insulating material. So whatever heat is lost from this point to this point, that is section BB to section A, along the length from section BB to section A, this we consider as length L. Whatever heat is lost in the radial direction, that we can calculate. See, that heat loss is through the insulating powder, mind that, not inside the rod, I mind that. We are assuming that temperature of the rod at the surface and at the center are same. That means temperature is same all along this cross section. Temperature is same all along this cross section. But from the surface, through the insulating powder, radially heat transfer is there. So whatever heat is lost from this point to this point, that heat transfer plus whatever heat is going out through this section A, if you sum total, that must be equal to the heat which is entering through the section BB. Is that okay?
স্যার আগুন একটু বলুন এইটা।
This is a rod. Heat is entering through this section BB. This is section BB. You can see B written here, BB. Even if you cannot see the cursor, at least you can see BB. Heat is going out, leaving through the section A. So we are making a heat balance. Whatever heat enters through section BB axially is equal to whatever heat leaves out through the section A axially, plus whatever is the radial heat loss through the insulating powder from section BB to the section A.
Yes, sir, got it.
That is a heat balance equation. So that equation is written here. You can see. You can see here Q dot BB, that is heat entering through the section BB, is equal to Q dot A plus this is the heat lost between section BB and section A in the radial direction. 2 pi KL, K is the thermal conductivity of the insulating powder, which is given here. L is the length between section BB and A. T12 minus T13 divided by log RO by RI. This is by হবে. This is not minus. This is divided by. Now this equation you will be able to see if you read the book by Incropera under steady state heat flow in the through a cylinder. Look at steady state heat transfer in a cylinder. There we will see that if you have a cylinder where you have a radius Ri and a RO, between the Ri and RO in the radial direction, the heat transfer in the steady state through a length L of the cylinder is given by twice pi K into L, where K is the thermal conductivity of the cylinder material. L is the length of the cylinder. This is the difference in temperature. I mean, inner temperature, outer temperature, divided by log of R outer divided by R inner. So this equation you'll see there. We have applied that equation. And Q dot A we have found out previously. So we can make this heat balance and make it equal to Q dot BB. Again, Q dot BB is equal to how much? Q dot BB is equal to, from the Fourier's equation, it is minus K BB, that is the thermal conductivity at this section BB, dt dx at BB into ABB.
স্যার ওটা কি মানে বিবি লেখা আছে কেন স্যার? এইচ এইচ এর মতো দেখতে লাগে।
হ্যাঁ মনে হচ্ছে, কিন্তু বিবি, কারণ আমাদের ছবিটা তো এ বিবি দিয়ে।
ওকে স্যার,
ছবিটাতে তো এ বিবি আছে, কাজে এইচ এইচ করতে আসবে।
হ্যাঁ স্যার সেটাই
ঠিক আছে। এইখানে তোমার এইখানে এই বিবি বিবি সেকশনটা দেখতে পাচ্ছ T5 যেখানে?
ইয়েস স্যার, হ্যাঁ দেখা যাচ্ছে।
এইখানে আমি heat transfer into through this section, it was the right side, সেটা হচ্ছে Q dot BB per unit time, that is equal to minus K at this location, that is at section BB, into area at section BB into dTdx at section BB.
Yes, sir. বোঝা গেছে এই কোশ্চেনটা।
এবার এই dTdx টা আমি বার করছি কি করে? আমি আগে যে t ভার্সেস x কার্ভটা এঁকেছি সেখানে এই পয়েন্টে আমি বিবি সেকশনের একটু আগে একটু পরে আমি দুটো পয়েন্ট নিয়েছি, নিয়ে আমি dt বার করেছি, dx বার করেছি, বিটুইন দোজ টু পয়েন্টস dt dx বার করেছি। dt dx is negative, so dt dx I get from the curve. So q dot bb টা আমি পেলাম by heat balance, that is q dot a plus whatever heat is lost between this bb section and a section. So with that we know the value of q dot bb. Again, q dot bb is equal to minus k into a into dt dx. So a we know, a is the area, dt dx also we get from the curve. So k at this section can be calculated. Okay?
Yes, sir.
Similarly, we go to section CC. Same exercise. This q dot bb, that is the heat which is flowing out to the section bb, plus whatever heat is lost between CC and BB sections in the radial direction through the insulating powder. If you add up, that must be equal to the heat which is entering through the section CC. So q dot CC is equal to q dot BB plus whatever heat transfer occurs in the radial direction between CC and BB. Come to this equation here once again. Q dot BB we have already determined, and q dot BB plus 2 pi KL into T10 minus T11 divided by log RO divided by RI, not minus. This is a misprint. K is the thermal conductivity of the insulating powder, that is equal to q dot CC. Again, q dot CC is equal to minus KCC into dt dx CC into ACC. That means this is the section CC. Section CC, whatever heat is entering, that is equal to thermal conductivity here minus K at this point, at this section, into dt dx at this section CC into area at this section CC. Now area at this section is known, dt dx at section CC is available from the curve between T and X, and K at section A CC can be determined from this equation, because q dot CC we have found out, that is equal to q dot BB plus whatever is the heat transfer between CC and BB in the radial direction. So with this we have been able to find out heat, thermal conductivity at section A, Ka, thermal conductivity at section BB, Kbb, thermal conductivity at section CC, that is KCC. Now, this section is at a lower temperature, this is at a higher temperature, this is at a much higher temperature, so the temperatures are also different. Now, if we plot a curve between the thermal conductivities along the y-axis and the temperatures along the x-axis, that is temperature at this, temperature at plane BB, temperature at plane A. If we plot along x, and if we plot the thermal conductivities along y, then we'll get a K versus T curve. That will tell us about the nature of variation of thermal conductivity with temperature. Is that clearly understood?
Yes, sir.
Now we come to this readings. We have taken these readings, and this is the readings based on which you have to make your calculations. Voltmeter reading, ammeter reading, room temperature, all are given. And this temperatures, this is T1 is 89. Mind that this is not 87, this is 89. Please take a note. T1 is 89, T2 is 86, T3 is 83, T4 79, T5 76, T6 73, T7 is 70, T8 is 67, and T9 is 64. These are all the 9 temperatures, 89 to 64. And T10, T11 are temperatures within the insulating powder. T12, T13 are also temperatures in the insulating powder. And T14, 15 are the temperatures of the entering and leaving water. This is T15 is T30, this is 31, T14 is 19. So with this, and how much water is flowing? Amount of cooling water circulated is 500 ml, and duration of cooling water flow is 80 seconds. 500 ml, taking the mass density, multiplying by the density, you can get this milliliter. There is a half liter rather per 80 seconds. So you can say mass flow rate also you can find out of water. So radial distance of thermocouples in insulating shell R is equal to 40 mm. This R I and this RO 60 mm. So with all this you can now make the calculations. Now you go to the sheets, plot the results. You have to give a sample calculation and plot the results showing temperature distribution along the length of the metal rod, conductivity as a function of temperature. This is your task. You have to fill up all these things. Date, you have to give today's date. This is the details of the rod, length of metal rod, 445 millimeter. Test length of the bar, 176 millimeter. All diameter is 25 millimeter. All these things are given, so you can easily do this thing. There a brief experimental setup description is given here. You can read. I have also explained. And this is the electrical panel, as I have shown in the previous experiment also, same panel. The ammeter, the voltmeter, and the temperature recorder, digital. And there are the selector switch, toggle switch, with which you can take the readings T1 to T14 here, T15 here. These are the experimental setup. So in your report, you have to give these sheets with the experimental setup, and you have to write the theory, and then a one-page sample calculation and the graph. All of you are there in the class, I suppose. Hello?
Yes, sir.
Yes, sir.
Nobody is supposed to leave before I end the class. So I think we have been able to understand the experiment.
Yes, sir.
Yes, sir.
Yes, yes. If you have any question, you can ask. No questions?
স্যার আমরা যখনই এরকম মানে কোনো ইয়ে কার্ভ, মানে যেমন স্যার এখানটায় টেম্পারেচার ভার্সেস সরি থার্মাল কন্ডাক্টিভিটি অ্যাজ এ ফাংশন অফ টেম্পারেচার যে গ্রাফটা পাবো স্যার, এটা তো একদম স্মুথ কার্ভ দিয়ে জয়েন করবো, তাই তো স্যার?
অ্যাকচুয়ালি মানে ডিস্টেন্স বিটুইন সেকশন এ বিবি সিসি যেটা আছে তাতে টেম্পারেচার ভ্যারিয়েশনটা তো অনেক। তুমি যদি দেখো, এখানে যদি দেখো, এই এ সিসিতে হচ্ছে টেম্পারেচার 89 ডিগ্রি সেলসিয়াস, আর T5 হচ্ছে 76, আর T1 হচ্ছে গিয়ে মানে T9 সরি হচ্ছে 64। তো এখানে হলো 89 থেকে 76 13 ডিগ্রি, আর এখানে 76 থেকে 64 12 ডিগ্রি। একদম স্ট্রেট লাইন হচ্ছে না ব্যাপারটা।
না স্যার, আমি স্যার টেম্পারেচারের সাথে
করে দেবে, হাতে টেনে স্মুথ করে দেবে।
না না স্যার, আমি এই গ্রাফটা বলছি না, মানে আমি থার্মাল কন্ডাক্টিভিটি অ্যাজ এ ফাংশন অফ টেম্পারেচার সেই গ্রাফটার কথা বলছি স্যার।
হ্যাঁ, সেই কার্ভটা আইডিয়ালি তো এটা স্মুথ কার্ভই হবে, কিন্তু আমি তো আর মানে আমি যদি প্রত্যেকটা পয়েন্টে ধরো এই T1 T2 T3 T4 প্রত্যেকটা পয়েন্টে থার্মাল কন্ডাক্টিভিটি রেকর্ড করি, করতে তো পারি।
ইয়েস স্যার।
করে আমি যদি কার্ভটা টানি হয়তো অনেকটা স্মুথ হবে কার্ভটা, কিন্তু যেহেতু এখানে আমি T1 এর পরে T5 এ চলে যাচ্ছি, T5 এর পরে T9 এ চলে যাচ্ছি,
মানে জাস্ট 3টে পয়েন্টই পাবো সেক্ষেত্রে।
3টে পয়েন্ট দিয়ে কার্ভ হলে কি করে সেটা স্মুথ হবে?
হ্যাঁ, স্মুথ হবে না। ওকে, মানে স্যার তাহলে আমরা একটা স্ট্রেট লাইন দিয়ে জয়েন করবো।
স্ট্রেট লাইন দিয়ে জয়েন করতে পারো।
ওকে স্যার।
ওকে,
ওকে স্যার।
so thank you very much, and I'll send this instruction sheet.
Sir, before you end up the class, can I show you something, sir, if you have some 5 minutes?
Yeah, I'll enter another class right now, but you tell me, you can tell me, no problem.
Sir, we have created the first graph. I mean the first graph of the experiment 1, sir. Sir, in that graph we had get a smooth curve. So can we just leave that graph as it is, or we should change it to a base fit straight line, sir?
Make it base fit straight line.
Okay, sir.
Okay.
Okay, sir.
So thank you for today, and this PDF I am going to send to you.
Okay, sir.
Maybe after 2 hours I'll send it. Okay.
Okay, sir. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Okay, end of today's class. Now you can leave, and I'll just request, as you have done the last day, please send a list of the real numbers who have attended the class today. And this is just for my own record, and I don't want to have a feeling that some of you are bunking the class. So please do not do it, because we are all mechanical engineering students. You also, me also. Though I am a teacher, I consider me as a student. So we are all same. So we should not, between us, we should not have any, we should have complete confidence. Don't bunk the class under any circumstance. If you feel that the class is of no use to you, or if you feel that the class is not interesting, you tell me. I mean, you can easily tell me. I'll make the class interesting. That is my job. I'll change myself so that the class becomes interesting to you. But don't just abstain from the class. I want you to attend the class. We are not meeting face to face, so even if we do not take the class online, then there will be no fun for having this course. So I want you to seriously study, and I want you to learn the subject. So please don't abstain from the class. And I'll request, as you have done so nicely, I'm thankful to you. I mean, this boy who has sent it to me. Today also, please, once again, you send the names, those who have attended the class, and I believe you, so send all the names who have attended. Okay.
Okay, sir. Thank you, sir.
Normally, in my class, nobody bunks. Normally, I have seen the last years, though I have done in online, everybody attended. So I've got that good feeling in my mind. Thank you very much.
Thank you, sir.